Welcome everyone. It's a great pleasure to introduce Rina. I know Rina since my undergrad days from IT Bombay. He then went on to MIT to do his PhD, but decided to come to Bay Area after his masters. So he worked in Cisco for some time, and he's been interacting with Rajiv group when he was at Cisco. At one point, he formally decided to go on and do a PhD, and he's just recently completing his PhD from Rajiv Motwani at Stanford in theory area, and he's going to be talking today about hashing, searching, sketching. I guess we're all interested in all of these techniques. So yes,
Thanks for giving me this opportunity to talk here at Google. I'm going to be talking about some recent results on hashing, sketching, and searching. So as we know, search has become a huge industry in the last few decades, and there is a wide variety of data type that we want to search on. There could be a simple search in a database where you have an input key and you're looking for something that exactly matches that key, an exact search. But in other cases, the search can be more complex. For example, if you're searching for similar documents or similar images or blogs or even geometric shapes or news articles, if you have an image search, then the input key, which is the image, is not expected to exactly match an entry in the database. So there, the search is more fuzzy. The similarity is defined at a more intuitive level. In more complex structures, the data could be hierarchical, so it's not just a flat structure. The fuzzy search, where you're looking for something similar, is often captured as a nearest neighbor search by mapping the object into a mathematical abstraction. The most common underlying techniques for search are hashing and trees. Now, when you have a search which is not an exact match, let's say you're looking for an image search, then one common method is to take the data object and map it, represent it in a mathematical format. For example, as a vector in high dimensions. So every image will become a point in, say, the Euclidean space. The way you do that is by, let's say, dividing the image into quadrants and then looking at the average color per quadrant. And that's how you get a feature vector. And often the number of dimensions that you get is very large when you take such an object and map it into a mathematical format. And then when you get a query point, that again becomes a point in that high-dimensional Euclidean space. And then the similarity search ends up becoming a nearest neighbor search. So you're looking for the point in this database of points which is closest to the query point. Now, such a problem of high-dimensional search suffers from what is called as the curse of dimensionality, which means that the problem is hard as the number of dimensions increases, which means either the search time is going to be exponential or the space requirement is going to be exponential. So finding the exact nearest neighbor in high dimensions is a very hard problem. And that is why algorithms researchers have settled for an approximate solution to the nearest neighbor search problem. An approximate in the sense that you're happy to find a neighbor which is within constant factor of the distance to the nearest neighbor. Say, for example, at most 5 times or 2 times the distance to the nearest neighbor. And this is often okay in practice because the most similar image is likely to be much closer than the other images, or this matching similar documents is likely to be much closer than the other documents, probably close by a constant factor. Now, a point in a high-dimensional space is only one of the mathematical abstractions that can be used to represent search objects, but there are many other. If you take a vector, you can either take the Euclidean distance, or you can take other distances. For example, you can take the L1 norm or an LP norm for different values of p. And depending on which norm you take, you will get a different notion of what is similar and what is dissimilar, a slightly different notion. So you have to be careful in picking your norm. Or you could use bitmaps, that is another common representation, and then use the Hamming distance between them. Or you could use strings, which is a natural representation for documents, and then use something like the edit distance. Or you can have sets. You can look at a document as a set of words and look at distances on sets. For example, the symmetric difference. Or you can use the earth mover's distance. The earth mover's distance is a distance measure on between sets of points, and it is given by the smallest amount of motion that you have to perform to transform one set into another. And trees are a natural representation for hierarchical data. Now, often there are ways of transforming one metric space into another. So all such mathematical abstractions with a distance measure can be thought of as a metric space. And there are ways to transform points from one metric space to another. And they tend to be distance preserving. That means the distances are almost preserved. So if you have a nearest neighbor search algorithm on one metric space, let's say the Euclidean norm, then it translates into algorithms for the other norms as well. So just an algorithm for nearest neighbors on one of these metric spaces seems to help in finding similarity search among all kinds of data objects by transforming them to these other metric spaces. And then there are also ways of converting any of these abstractions into a bit vector, into a very short bit vector, which again tends to preserve the distances. And this is called as sketching, where you can take a big, huge object such as an image or a document and convert into a few number of bytes, a small number of bits, so that the Hamming distance between this final bit representations indicates how close the original documents or images are. So I'm sure you're all familiar with this when you're looking for similar documents. You probably know that it is possible to compress a document into a few bytes and still tell by looking at the few bytes which documents are similar to this document. And that is called as sketching. So as we saw, sketching is the art of taking large complex objects and compressing it into a few bytes or a few bits, so that by looking at these sketches, you can tell how similar or how far apart the original objects are. A Bloom filter is a type of a sketch of a set. So it takes a huge set and then compresses it down to a small representation. And it can be used for approximate membership queries. So you can tell by looking at that short representation with high confidence whether or not something is a member of this set. And it's very useful in storing a large set on chip, in memory, and answering with high confidence if an element is present. And if you want to perform some action, if the element is present, then only if the on-chip computation says yes, then you go off to the disk and you do the full computation. A related notion is locality-sensitive hashing. So you probably all know that hashing can be used for an exact match, where you take a key and you use a hash function to map it onto a bucket. And then if an element from the database is present in that bucket, you will exactly find it in the same bucket. But there is a method to use hashing that can be used for approximate search, for nearest neighbor search. And that is called as locality-sensitive hashing. And the idea there is that it tends to hash nearby points to the same bucket. So it's likely to hash nearby points to the same bucket, and it's unlikely to hash far-off points to the same bucket. So it's slightly different from sketching. Sketching maps similar objects to the same bitmap. Sorry, it maps similar objects to similar bitmaps. Bitmaps which have very small distance between them. Whereas locality-sensitive hashing tends to hash similar object to the same bucket or to the same value. So they are similar notions, but not exactly the same. And then the techniques of hashing and sketching are also commonly used in what is called as streaming algorithms. A streaming computation involves, in streaming computations, you have an incoming stream of objects, large number of objects, and you want to perform some computation. Say, for example, finding the most frequent element in the stream. And the constraint is that you don't have a huge amount of space to remember all the elements. And that is why you need to store a summary of what you have seen so far, a concise summary of what you have seen so far. It's just enough to make that computation. Say, for example, finding the most frequent element. And that is why techniques of sketching and hashing are commonly applicable here. So as we all know, even for exact match, hashing is one of the most classical techniques. It's very easy to implement. And the most common problem you run into is collisions, when many items hash to the same key. So the hope, of course, is that your hash function is random enough so that different items will hash to different buckets, or the distribution of items into buckets is about uniform. But then if you run into these collisions, then you have to resolve them, say, by using linked lists, and that increases your search time because you have to traverse over the linked list. So you can reduce the number of collisions by increasing the size of the hash table. But then that takes space. So there's a natural space-time trade-off here. Now, the most common way to analyze hashing is to analyze them in terms of balls and bins, where you think of the bins as the buckets and the balls as the items. And the hash function essentially takes each item and maps it onto a bucket. But if the hash function is random, then you can think of it as you're taking an item and throwing it into a random bucket if you use a pseudo-random hash function. So what you're interested in here is how even is the distribution of balls into bins, or how even is the distribution of items into buckets. Now, this framework has been analyzed in detail in algorithms research, and it is well known that the maximum bin, if you take n balls and if you randomly throw them into n bins, you take each ball and throw it into a random bin, then the maximum load is given by log n over log n. That means this is the length of the longest list, the maximum number of collisions. Now, it turns out that you can make a huge improvement in the distribution of bins by making a small change to your hashing process. Small change to this balls and bins process, the way you're throwing the balls. And that is as follows. Instead of taking a ball and throwing it into a random bin, you pick two bins at random. Instead of picking one bin, you pick two bins at random and throw your ball into the smaller of the two bins. So just that small change gives rise to a lot more even distribution of the balls into the bins. In fact, the improvement is exponential. The maximum load drops exponentially from about log n to about log n. Or another way to understand this is look at the probability that a bin has a certain load. What is the probability that a bin has a certain load? I. In the earlier case, when you're throwing a ball into a random bin, the probability is exponentially small in I. It's about 1 over 2 to the power I. But now, if you use two bins and put in the smaller of the two, it becomes doubly exponential. It becomes 1 over 2 to the power 2 to the power I. So the probability of exceeding a certain load drops exponentially. It drops by a huge amount. So the distribution is a lot more even. Now let's try to understand why you get this exponential improvement. Why is it that just by taking 2 bins and putting in the smaller of the two, you get an exponential? One would think that you would get a quadratic improvement or something like that. Why is it exponential? And the reason is as follows. Let's try to recursively compute the fraction of bins with a certain load I. Let's call that Pi. Now, how can you ever get a bin with load I plus 1 when you're doing these 2 balls and putting it into the smaller of the two, when you're choosing these 2 bins and putting the ball into the smaller of the two? The only way you can get a bin with load I plus 1 is if both the bins that you chose have load at least I. If even one of them had a load of I minus 1 or smaller, you would put it into the smaller one. And so you will not create a bin with load I plus 1. So the only way you create a bin with load I plus 1 is if both those bins that you chose have load I, which means the probability of that happening is about Pi squared. And so the fraction of bins with load I plus 1, which is Pi plus 1, is about Pi squared. So this gives you a rough recurrence on how Pi grows. And if you start with P of 0 is P of 1 as some constant, and if you keep chasing this recurrence, then you will get that P1 is half squared, and then P2 is half squared squared, and P3 is half squared squared squared, and so on and so forth. So by the time I becomes about log n, you will find almost no bin with load of log n. So that is why you get this exponential improvement. Any questions here? Because you really need to understand why this is, why this is so much better than log n. Does anyone have any doubts about this? I mean, it's a lot better when you look at the numbers. If you look at, if you let's say you want to find what is the probability that a bin contains 5 balls, and if you plug it into the old scheme, you will get that the probability is about 1 over 2 to the power 5, which is 1 over 32. But if you try the new scheme, the probability is 1 over 2 to the power 2 to the power 5, which is 1 over 2 to the power 32, which is less than 1 in a billion. Yes?
So two choices. What if you tried, like, I don't know, n number of choices?
Exactly. So that has been well studied, and it does not become log of n. So it stops at 2 logs. But you get a denominator. You'll get a log n divided by a log d. So you'll get slightly decreasing denominator. So if the probability here is about 1 over 30, then here it's about 1 over a billion. Let's look at some of the results we'll see in this presentation. We'll see a new result on hashing with exact match using a variant of this balls and bins processes. We'll show how to get about 85% space utilization of the hash table. So we'll show how you can get a maximum load of, actually a constant maximum load, not even log n, a constant maximum load. And we'll show how you can arrange, you can perform inserts and deletes, and you don't even have to resort to linked lists for resolving collisions. And you can still maintain about a very high space utilization. We'll also mention a result on Bloom filters, which improves upon the classical Bloom filters by a small constant factor in terms of space complexity. And then we look at hashing for nearest neighbor search, which is locality sensitive hashing. And we'll see a variant of locality sensitive hashing that uses very small amount of space. And we'll see how ideas from there can also be used in KD trees, which is a very commonly used data structure for similarity search. And we'll might also look at some lower bounds for nearest neighbor search using locality sensitive hashing. And if time permits, we will look at some algorithms for sketching of hierarchical data and some results on finding frequent elements in a stream. So first, let's look at the result on exact match using hashing. So as we saw, instead of hashing an item to a single bucket, if you hash it to 2 buckets and put it in the smaller of the 2, then the distribution of items into buckets is a lot more uniform. The bucket containing them with the maximum number of items will have about log n items. And you can actually, and then every search will look in both the buckets that an item hashes to. So every search will involve 2 reads. And you can actually parallelize your memory operations by dividing the hash table into 2 parts, and then parallelly reading or writing into both the parts. Now, note that since your search is looking at both the buckets that an item hashes to, each item could reside in any of the 2 buckets that it hashes to. So even if you initially placed an item into this bucket, because that bucket was of the smaller size, in future, if the size of that bucket increases, you always have the option of moving it to the alternate bucket. And things still work because the search is always going to look in both the buckets. So if you can exploit this fact and perform such moves, then maybe that can result in a better distribution of items into buckets. So the idea, yes?
I apologize. Just to make sure I'm clear, you would have to rehash that object, right? Because the 2 buckets aren't linked by themselves.
Yes. So you can find both the buckets by just hashing that object. Yes, you're right. But the basic concept is that just because you place an item in one bucket, you always have the option of moving it into its alternate bucket. And what we show is that indeed it's possible to get a huge improvement by performing such moves during inserts. By performing such moves, you can actually maintain a maximum load of 2 items per bucket. That means the distribution is so even that most of the buckets will have exactly 2 items. Some of them will have 1 item, and some of them will have none. So what this means in terms of hashing is that you don't even have to implement any linked lists because you can pre-allocate 2 items per bucket. And with high probability, you will never experience an overflow. Yes?
We're still talking in bins and items?
So we'll show that it's possible to pack more than n items into n buckets.
I was just curious how you were getting more than, how most of the bins would have 2 objects with still same number of items and keys, or other items and buckets.
Oh, actually, it's closer to 2n items. Okay. It's actually close. We show that we can pack 1.6 n items into n buckets.
Right.
So if you pre-allocate 2 per, yes.
How much work do you have to do each time in order to do
Yes.
this rebalancing?
Yeah, so let me get that. So every time, the number of moves that you perform is constant in expectation. And with high probability, the number of moves is no more than log n. And then we also have we'll also see result where what if you only want to do 1 move? What if you don't want to do more than 1 move? Then you will see that you'll get a slightly lesser improvement, not as good as this. So by performing such moves during inserts, you can get a very high space utilization out of the hash table by pre-allocating location for 2 items per bucket. And the space utilization is about 85%. And of course, every read involves every lookup involves 2 memory accesses, and so for inserts. And you don't need any dynamic allocation. As I said, with high probability, log n moves, and constant in expectation. And this idea has been used before, but not with slightly weaker results in cuckoo hashing by Pag and Rodler. Yes?
So the 2 items per bucket, is that with high probability, or is it 2 items per bucket?
With high probability, you will never experience an overflow.
Okay.
So if you try to insert 1.7 items, 1.7n items into these 2n location for 2n items, with high probability you will never experience an overflow. So this was actually inspired from work on routers where you're searching for IP addresses for forwarding. So you have a hash table of next hop IP address, and you're doing an exact match. And there it's very critical that that your memory bandwidth is low, and your parallelism is high, and also you don't want to do much allocation, dynamic allocation. So that's where this work came from. And then, as you said, the overflows, there are ways to take care of those overflows in that context by just keeping a small on-chip CAM for a few entries. And it turns out that it's not more than 20 or 30 entries. So let's try to understand, let's try to analyze this arrangement of balls and bins and understand how these moves occur pictorially as a graph. So the way you view it as a graph is you think of the bins or the buckets as nodes, as vertices. And then you can think of a ball. A ball is picking 2 bins at random. So that becomes an edge, because you can just put an edge between those 2 bins that it chose. So each ball can be represented by an edge. And then you have to take the ball and put it into one of those 2 bins. And that choice can be shown by an edge. So the balls and the bins and the bin choices for every ball can be represented by a directed graph. And whenever there is an arrow pointing into a node, that means that contributes a load onto that node. So the total load on a bin is the in degree of that bin. And what is a move? Let's say you're trying to insert a new ball into the top vertex there. Then you have the option of moving this ball from that vertex to this vertex, because you could have chosen either of those 2 vertices. So you always have the option of moving it. And what that translates into is flipping the direction of that edge. So the vertex u, the load of the vertex u decreased by 1, and the load of the vertex v increased by 1. And you can take the new insert and insert it into u. And you can actually cascade such a sequence of moves. Let's say you're trying to insert a new item here. You can take this ball, move it from this bin to this bin, and then take this separate ball, move it from this bin to this bin, and this ball, move from this bin to this bin. And then perform the new insert here. So that leaves the load of all these 3 vertices unchanged, and only the load of this vertex increases by 1. That means even though you performed the insert into this node, its effect was felt only by this node. Yes?
You have to assume it's a graph, or is it multi-graph, everything just follows through?
We analyzed it for a graph. I believe it should not be hard to extend it for multi-graphs. So in general, you can perform such a sequence of moves along directed edges while going backwards. So if you're trying to insert a new ball into this node, you perform a backward search by following directed edges and find the least loaded bin among all the bins that you can reach in this fashion. And then perform a sequence of moves. Let's say, for example, you find that the least loaded bin was this node. Then you can perform a sequence of moves and then perform the final insert in U. And what that does is essentially puts the load of the new insert into this least loaded bin U, into this least loaded bin V. So it suddenly increases the space of bins where you can essentially transfer the new load. So earlier you were just putting in one of 2 bins. Now you can actually choose any of these bins to to take the effect of the new load. Yes?
So, excuse me. Is there any way to utilize the bins that are empty and don't have any edges connected yet?
Well, yes. For example, if this bin is actually empty, if you look at this bin, although there is an edge here, the load of the bin is 0 because the pointer is pointing this way. That means this ball could have gone either here or here, and it was chosen to be placed here. So the empty bins are the ones which have 0 in degree. So that's the insert algorithm. You hash your, yes?
Even to do this search, detecting every edge takes 2 hashes, yes?
Yes.
So just to look at this graph, you need something like 30 hashes?
You need, yes, you're right. It turns out that it's about log n hashes is what you need. So the depth of the tree that we look at is about log n with high probability. So in expectation, it's constant, which means with high, typically you will find an empty bin or a bin with load at most 1 by the time you just search at level 1. You just have to look at the children of the top node. Most of the time, you just have to do depth 1, and then once in a while, very rarely, you will have to go down further. So that's the search algorithm. You hash your item into 2 buckets, into 2 bins, and then perform such a backward search by traversing directed edges, and find the least loaded bin that you find, and perform moves so that the load of that least loaded bin increases by 1. And what we show is that it's possible to maintain a maximum load of 2. So you can keep performing inserts, always find a bin with load at most 1, so that when you perform the new insert, the load will become at most 2. So the claim is that you can always find a node with load at most 1 by performing such a breadth first search along directed edges. Now, let's see how many items can you pack? How many items can you keep putting so that the maximum load is still 2? So to analyze that, observe the graph and ignore the directions for a moment. Now the graph is a random graph because every ball is picking 2 bins at random. So every edge is placed randomly. So the graph is a random graph. And let's try to see when can an insert operation fail. That means under what circumstances will you fail to find a bin with load at most 1. The only way that can happen is you're performing such a search, a breadth first search, backward search, and you never find a bin with load 1 or less. That means every bin that you find has load at least 2. The only way that can happen is you start with the top node, and that has in degree 2. So you have 2 edges pointing in. And then both the nodes that you came to, both of them have in degree 2. So they also have 2 children each, and so on and so forth. So you always find 2 children. That means you are finding this complete binary tree embedded in this graph while you're performing this search. So the only way your search can fail is if there is such a complete binary tree embedded in the random graph. So the question becomes, for what values, how many edges, under what conditions is such a complete binary tree present in a random graph? What is the ratio of the number of edges to vertices so that this does not happen? And we can actually compute the probability recursively. The probability that such a deep binary tree is ever present in a random graph, that probability can be computed recursively in terms of the height, in terms of the depth of the tree. And we show that as long as the number of edges to vertices is less than 1.67, as long as the edge to vertex ratio is no more than 1.67, there can never be a binary tree of depth more than log n. That means as long as the occupancy is less than 85%, by the time you search to a depth of log n, you will always find some node with load at most 1. And that's why your insert will succeed. And that gives us the 85% space utilization. Any questions? And then I also mentioned that you don't have to you don't have to be willing to perform a large number of moves. Yes.
How tight is the error analysis of log and depth?
How tight is the? You mean in terms of?
Can you reduce Can you reduce that length and still have max load of 2?
Exactly. So that's what I'm coming to. You have a trade-off between the depth of the search and the maximum load. So if you're willing to perform a search up to a depth of log n, then you can maintain a maximum load of 2. But even if you're willing to search to a depth of 1, you still get an improvement over not performing any moves at all. So you're performing a depth of h, up to a depth of h, then the maximum load is given by this. It's about log n over h and log n over h. So even if h is 1, this is about log n divided by triple log n, which is asymptotically better than just picking 2 bins and putting it in the smaller of the 2. Yes?
Still, I think the same question that you mentioned, that there are no multiple edges, which means that we assume that no 2 balls are hashed into the same pair of buckets.
Oh, okay.
Is it really a valid
Sorry. I think I got confused when he asked, is it a multigraph? We do allow multigraphs. So you do allow parallel edges. So that's not an issue at all. It's very easy to. In fact, the analysis is for allowing such edges, parallel edges. Yes?
Seems like bad luck could force a bin load of 3 with as few as 2 bins, 5 objects.
2 bins.
So we can only transfer a ball to another bin if there's already an edge there.
Yes.
So no matter how big our bin space is, bad luck can force us to use a small subset of that as we like.
Well, that's only if there are lots of edges in that small subset.
Right. So I could give you 100 bins and then say, oops, the dice forced everything into these 2.
Well, the probability of that is extremely small as.
Well, so yes, it's small, but it's not always.
Well, what we show is that the probability, if you have n balls and n bins, or if you have 1.6 n balls and n bins, then the probability that this will fail is something like 1 over n squared. That means if n is 1,000,000 or 1,000, then it's 1 over a million squared. So of course it can. We're not saying that it can never happen, but if you look at the expected number of overflows, as I said, in the example where you're willing to place an internal cam, the expected number of overflows is about 20 or so. I mean, even 20 is extremely unlikely. So just by placing a small on-chip cam, you get a much more efficient search component. Yes?
How tight is this big O? I is big O of this?
This big O in the analysis is not very tight, but but just for 2 balls and bins, it's very tight. It's actually log n plus constant. It's log n plus O of 1. This, in the theoretical analysis, it's not very tight, but I'm pretty sure in practice it's very tight. In all these balls and bins processes, very often there is no multiplicative constant. There is only an additive constant. So that means even if you perform a small number of moves, just performing 1 move will give you an asymptotic improvement. And 1 move is very easy. You just have to take the 2 bins and compare it with each of their children. And then, as I had mentioned, all these methods of multiple choice hashing can also be used to get a better construction of Bloom filters, which beats the classical Bloom filters by a small constant factor. I won't mention the details. So having looked at hashing for exact match, let's now move on to hashing for nearest neighbor search, which is called as locality sensitive hashing. Any questions before we move on? So as I said before, it's possible to take objects, search objects, and then map them into some mathematical space, for example, the Euclidean space, and then you're performing a nearest neighbor search in this Euclidean space. And you're not insisting on finding the exact nearest neighbor, but you're okay getting an approximate nearest neighbor. So let's say we are looking for a C approximate nearest neighbor, where you're happy to find any point which is within at most C times the distance to the nearest neighbor. Or another way to look at this is think that your nearest neighbor, there's a huge gap between the distance to your nearest neighbor and to the other points. Let's say there is a factor of C gap. In that case, finding the C approximate nearest neighbor is same as finding the actual nearest neighbor who's much closer than the other points. And let's say you know what that distance, you know the search radius. Let's say you have some estimate on that search radius. Let's say you know that your nearest image has to match this image on at least so many pixels, or you have some estimate of that sort. So let's assume that you know that, have a handle on that distance, on that search radius. Now, one of the most traditional methods for performing nearest neighbor search is by using KD trees. So it's exactly like the classical tree, except that it partitions the space along the different dimensions. So first it'll partition along the x-axis and choose half the points here and half the points there, and then choose another plane along the y-axis and so on and so forth, and it gets a tree of about log n depth. Now it's if you analyze the KD tree performance in high dimensions, even slightly higher than, even in dimensions which are slightly more than 2 or 3, it turns out that the probability of finding the nearest neighbor, or even an approximate nearest neighbor, drops a lot as you increase the number of dimensions. So even by the time the number of dimensions is 3, even then it's quite possible that you will not end up finding the nearest neighbor as you perform the walk down the tree. And that is because since you have so many dimensions, since you're walking along so many of these cutting planes, it so happens that the query point and its neighbor get split by this cutting plane, especially if the number of dimensions is large. So let's see how can hashing be used for performing nearest neighbor search. Is there a way of hashing these points so that nearby points tend to map to the same bucket? And one way to do that was shown by Indik Motwani, which is as follows. You take a random hyperplane, and you take periodic shifts of that hyperplane, and you take another random hyperplane with the random orientation, you take periodic shifts of that one, and keep doing that. And that will essentially divide the space into cubes. And if you look at this partitioning, and if you look at two nearby points have a much better chance of falling into the same cube as compared to far off points. So this is the hash function. You think of each cube as a bucket. Yes?
In order to get normalized, I want to understand in how many dimensions do you do this?
Well, it turns out that you do need about log n dimensions. We are talking about very high dimensional space.
When n is the number of points.
N is the number of points. So by the time you do this log n times.
And in each dimension, into how many sections do you divide?
Well, these sections are, conceptually, there are an infinite numbers of such hyperplanes, but most of them will be empty.
Yeah, so I mean, how many will be filled?
Well, not more than n for sure, because it goes at n points. And the periodicity, the interval length is given by that estimate r. So if you think of r as 1, then this is 1. You choose this length in such a way that that nearby points, that means you and your nearest neighbor, are likely to fall in the same in the same interval, and far off ones are unlikely to fall in the same interval.
When you say likely, it means 3/4 or 1.
No, so that's what I'm getting into. The probability is actually very small.
Okay.
The probability of nearby points, you and your nearest neighbor falling in the same bucket or same cell, is around n to the power minus 1 over c, where c is the approximation constant. So if you're looking for a 2 approximate nearest neighbor, then the probability is 1 over square root n. But if you take far off points, then the probability of falling in the same bucket is about 1 over n. So there is a huge bias for nearby points falling into the same cell. So the probability is high, but it's not like constant. It's not 3/4 or 1/2. It's much more than the probability of far off points falling into the same bucket. So as I said, the probability that the query point and its nearest neighbor fall into the same bucket is about n to the power minus 1 over c. So in order to amplify this probability, you can use n to the power 1 over c such hash tables independently, and then perform your hash lookup in all of these. And then with high chance, you will find your nearest neighbor. So the space complexity is about n times n to the power 1 over c, and the query time is about n to the power 1 over c. Now this division of the space using hyperplanes is only one possible locality sensitive hash function, but there could be others. The only criteria that a locality sensitive hash function needs to satisfy is that nearby points are likely to go to this, are more likely to go to the same value as compared to far off points. So formally, a locality sensitive hash function is defined by, if you have 2 points which are separated by a small distance, then the probability that they hash to the same value is at least above some threshold m, and the probability that far off points go to the same hash value is small. It's smaller than some threshold g. And what Indek Motwani showed is that if you have such a locality sensitive hash family, then you can construct a data structure for nearest neighbor search with space n to the power 1 plus rho and search time n to the power rho, where rho is given by a function of these bounds on the probabilities. And then if you analyze, you perform this analysis, you plug in into this framework the hyperplane based locality sensitive hash function, then you can actually compute these probabilities, and it turns out that the rho is about 1 over c. And that is why you can perform a search in time n to the power 1 over c and with space n to the power 1 plus 1 over c. Any questions here? So basically they make n to the power 1 over c copies, independent copies of such hash tables. Now the new result that we show is that you don't need to have so many different hash tables. So think of c equal to 2. What their method is saying is that you need space of n root n. You need about root n hash tables. So if n is large, then this can mean a huge amount of space. What we show is that you don't need so many hash tables. It's sufficient to just work with one hash table. You work with one hash table, but the difference is that instead of searching for the query point in the hash table, you look for random points in the neighborhood of the query point into the hash table. And you do that many times. And what we show is that with a good chance, you will find the nearest neighbor of the query point. So instead of searching for the query point, you take a ball of radius r around that query point and pick random points on this ball, and then search for those that in the hash table. That means hash those points and go to the bucket where they go and look for and see the distance to q. And among all those, find the nearest point nearest to the query point. So instead of searching for q, you're just perturbing q by a small distance and looking for those points. And yes?
You do it once or you do it many times?
We have to do it many times. So the query time is about n to the power 2 over c. That means you have to do it about n to the power 2 over c times. So let's try to analyze how many points we'll have to pick in this ball. How many perturbations of q do you have to search in this hash table so that you can find the nearest neighbor?
On the ball or in the ball?
Repeat that?
On the ball or in the ball?
On the ball.
So what happens if your nearest neighbor was your query?
Repeat that, sorry?
What happens if your nearest neighbor was in fact your query? You had an exact match.
You are right. Well, for the analysis, we say on the ball. It doesn't matter. When you're talking about high dimensions, when you're picking random perturbations, it can be shown that most of the points are, if you're talking about a point at distance r, if you have the handle on the distance r, then most of the points are on the ball, exactly on the ball. If you have an estimate on the distance to the nearest neighbor. So let's try to understand how many points you'll need to pick on the ball. So Q is the query point, and these are the cells that you get by your hyperplanes. And the nearest neighbor is some point on that ball because it is at distance r from the query point. And it is essentially a random point on that ball. Why is it a random point? Because these hyperplanes have random orientations. So you can think of the nearest neighbor as some random point on the ball. So how many random points do you need to query till you find some point in the same cell as the nearest neighbor? And it turns out that to find the number of points you need to query, the number of points is related to the entropy of the cell where the nearest neighbor P lies, given the query point and the hyperplanes, which is intuitive. So it's intuitive that what the amount of missing information is the entropy of the cell of the nearest neighbor, and it's related to this quantity. It's actually exponential in this quantity. To understand this more clearly, just look at this lemma. We are essentially asking that you have a random variable which can take some values from a certain distribution, and how many times do you have to sample values from the distribution till you hit upon the correct value of the random variable? So if a random variable has a uniform distribution, let's say it can take n values with equal probability, then the number of samples you have to take till you hit upon its correct value is about n. More precisely, it's exactly n log n with high probability. If you pick n log n samples with high probability, you'll get the correct value by a coupon collection argument. But then if you look at the entropy of that distribution, then the entropy is log n. So the number of samples that you have to perform seems to be exponential in the entropy of the distribution. And that holds in general. If you have a non-uniform distribution on a random variable, to guess its correct value, the number of samples you have to make is about 2 to the power entropy of the random variable. Yes, you have a question? So here you are trying to guess which neighboring cell the nearest neighbor lies in. And by that lemma that I just showed, the number of samples you have to make is 2 to the power the entropy of the cell value of a random point on that ball. And so you can actually estimate the entropy. You can actually compute the entropy, and it turns out to be about twice log n over c. And if you plug it in, you get a search time of about n to the power 2 over c. So if you sample so many points, you will find the nearest neighbor with high probability. And you can actually estimate the space requirement in practice. If you have 1 million points, you need to store only one hash table, and you don't even need to store the entire object in the hash table. It's sufficient to store a sketch of the object, because the sketches are sufficient to tell you how similar or dissimilar it is from the query point. And the sketches are very small. It can be done in about 8 bytes per object. And so even with million, even for 1 million objects, the space requirement comes out to be about 5 megabytes. sorry, 5 bytes per object. So it comes out to be about 5 megabytes, which is a very small amount of space for nearest neighbor search. So we also get an alternate formulation of the locality sensitive hash function, where instead of stating it as probability bounds on items hashing to the same bucket, we'll say we in fact put a bound on the entropy of the hash value of the nearest neighbor given a query point. And we get an alternate formulation where the rho is a function of that entropy and the probability bound on far off points. And the search time is about n to the power rho, and the space is linear. Now the same algorithm of the new algorithm that we saw on locality sensitive hashing can in fact even be used on trees, on KD trees. So even if you have a KD tree, you get a huge improvement by not searching for the query point in the KD tree, but by searching for points, random points in the neighborhood of the query point. So if you just take a traditional KD tree in d dimensions and take the query point and search for the nearest neighbor, the probability that you'll not find the nearest neighbor is very high. The probability of finding the nearest neighbor drops exponentially in the number of dimensions. It's about e to the power minus d over c. Now this is for a random database of points. If you take a database of points randomly distributed in a unit cube in d dimensions, and if you plant a nearest neighbor, which is at 1 over c to the distance to the other points, then the probability that you will find the nearest neighbor is very small as number of dimensions increases. So even if c is 2 and d is 4, the probability is about 1 over e squared, which is 1/10. That means 90% of the time, the KD tree search algorithm can fail in finding the nearest neighbor. But if you just make that small modification of don't just look for the query point itself, but look for many points in the neighborhood of the query point and search for those, then with high chance you will find the correct nearest neighbor. And how many points do you have to choose in the neighborhood of the query point? It's about e to the power d over c. So if this probability was 1/10, what we are saying is you just take 10 random points, what we are saying is take 10 random perturbations of the query point and search for those in the tree. And then you've got a much higher chance of being successful in finding the nearest neighbor. And that is actually verified by using simulations. Even in 3 dimensions, if you choose c equal to 4/3, then if you take a typical KD tree search algorithm, then with 25% cases you will fail in finding the nearest neighbor. And that can be amplified all the way to 90% by just taking 5 random points in the neighborhood. And that probability, the failure rate is even higher with KD trees. If you take 5 dimensions, then the probability of finding the nearest neighbor is about 50% for this value of c. And that can be amplified all the way to 90% by choosing more points. And it gets even better for higher dimensions. So it's just a simple, small change to the KD tree search algorithm, but gives a much better result in terms of finding the nearest neighbor. And you don't even need to modify all the code base. All you have to do is call the search routine a few times with points which are variants of the query point. Any questions? Now, how am I doing on time? Okay, let's wrap up. Let me just go over this, skip over this lower bounds. This is essentially saying that recently there was an improvement on locality sensitive hashing for nearest neighbor search in Euclidean dimensions, where the rho value was improved from 1 over c to about 1 over c squared. And the way they did that is by, instead of using hyperplanes based partitioning of the space, they used spheres, a spherical partition of space into buckets. And that gives a much better improvement. And the reason it gives an improvement is because the spheres have the smallest surface area for a given volume. And so the chance that nearby points will get separated by a sphere is small. But what we show is that lower bounds which match those upper bounds. So what we show is that these are indeed the best possible partitions of space for nearest neighbor search. And besides that, let me also mention a result on sketching algorithms for trees. Some of you might be familiar on sketching algorithms for sets. If you have a large sets, there are ways to perform a sketch, take a small sketch, by using what is called as a min hash. You hash all the items and you take the value which has the smallest hash value. And what we show is that there's a way to generalize that to trees, where the objects are not just arranged in a flat set, but where the objects are arranged as a hierarchy, in a hierarchical fashion as a tree. And it's possible to generalize the min hash algorithm to get sketching algorithms for trees. So in conclusion, we saw some space-efficient algorithms for exact match using hashing by using balls and bins. And then we saw how a result on Bloom filters, how balls and bins variance can be used for getting Bloom filters. And then we saw nearest neighbor search using locality-sensitive hashing. And we also mentioned some algorithms in sketching. That's the end.